Our topic is Solution Approaches to Linear Programming Problems, Part 1. As I have mentioned, there are two ways of solving a linear programming problem, by the graphical and by the simplex method. First is the graphical method. As the name implies, this method makes use of graphs to arrive at the optimum solution. The optimum solution is a solution that makes the objective function as large as possible in case of the maximization process and as small as possible in the case of minimization process. The set of all points in the graph satisfying the constraint is called the feasible solution. And these points are located where? At the feasible region. Again, there are two main parts of the linear program: the objective function and the constraints or limitations. Okay, again, there are two parts of constraints. We have the explicit and implicit, where explicit constraints are conditions of the problem which are expressed in mathematical sentences, and implicit are those that are implied. Okay. The steps to follow in using the graphical method. First, represent the unknown in the problem. Tabulate the data about the unknown, so if necessary. Formulate the objective function and constraints. Graph the constraints and always solve for the coordinates at the point of intersection of lines. Substitute the coordinates at the vertices of the feasible region in the objective function. Then formulate your decision by selecting the highest value of the objective if it is maximization and the lowest value if it is minimization. For our example problem, the Morgan Furniture makes two products. We have tables and chairs, which must be processed through assembly and finishing departments. Assembly department is available for 60 hours in every production period, while the finishing department is available for 48 hours of work. Manufacturing one table requires 4 hours in the assembly and 2 hours in finishing. Each chair requires 2 hours in the assembly and 4 hours in finishing. One table contributes 180 to profit, while a chair contributes 100. So the problem here is to determine the number of tables and chairs to make per production period in order for us to maximize the profit. Okay? So let us solve for this problem. Okay, first is, represent the unknown in the problem. So we have here, let X be our number of tables and Y the number of chairs. Okay, so there are two processes. We have the assembly and the finishing. And of course, you are also given the profit. So for the tables, for the table, it requires 4 hours in the assembly and 2 hours in the finishing department. For the chair, it requires 2 hours in the assembly and 4 hours in the finishing department. So the assembly department again is only available for 60 hours in every production period. So that is less than or equal to 60. So for the finishing department, it's available for how many hours of work? 48. So that's also less than or equal to 48. Okay, why is it less than or equal to? Because this is the available number of hours only. Okay? Then for the profit, the table contributes how much? 180 pesos to profit, while the chair contributes 100. Okay? Then we can now formulate the objective function and constraints. So we have here, for the objective, that is to maximize, let us say our profit is Z, that is equal to 180x plus 100y. Okay? Subject to, what are our constraints? For the explicit constraint, we have 4x plus 2y is less than or equal to 60, and we have 2x plus 2y is less than or equal to 48. Of course, for our implicit, we have x and y is greater than or equal to 0. Okay, so let us get the coordinates for our graph. So let's say this is, okay, we can divide this by 2, both of these inequalities. Let's make these equations. We have 2x plus y is equal to 30, and we have x plus, this is 4. 2y is equal to 48. It's 24. Okay, 24. Okay, I have divided it by 2. Okay, so here, what are the coordinates? If x is 0, y is 30. If y is 0, x is 15. For this one, if x is 0, y is 12. And if y is 0, okay, x is 24. Okay, so let us graph the constraints. Okay, so for this one, we have, let's say this is 5, 10, 15, 20, 25, 30, 35. Okay, let's say that's our graph. Okay, let's say this is 5, 10, 15, 20, 25, 30. Okay, then we have here, okay, so we have 5, 10, 15, 20, 25, 30. Okay, this is our x. Okay, then for our first line, we have there 0, 30. Okay, and 15, 0. So this is our first line. Okay, so that's our first line. Next is 0 and 12. Okay, and then 24 and 0. Okay, so this is our second line. Okay, so you have it there. Okay, so the first equation is what? That's less than or equal to. That's our first inequality. So we shade this like this. Okay, and also our second inequality is also less than or equal to. So let's shade this. Okay. Okay, so what is our feasible region? It's this one, this area. Okay, this is it. Okay, so this is our, okay, so this is our 2x plus y is less than or equal to 30. This one is our x plus 2y is less than or equal to 24. Okay, so this is our feasible region. Okay, so what are these vertices? Okay, so we have here, okay, we have 15, 0. Okay, let's list it down. 15, 0, this one. Okay, and then we have 0, 12. Okay, 0, 12. What about this point? Okay, so what about that intersection? Okay, let's solve for that. We have, okay, by elimination method, 2x plus y is equal to 30. X plus 2y is equal to 24. Okay, so let's eliminate. Okay, 2 and x. Okay, we have here 1 and 2. We have 2x plus y is equal to 30, and 2x plus 4y is equal to 48. Okay, so let's eliminate that. We have that now. 3y is equal to negative 3y is equal to negative 18. So we have here y is equal to 6. Okay, so if y is 6, what is x? So let's say this one. Okay, in this equation, we have 2x plus y is equal to 30. If y is equal to 6, then x is what? 2x plus 6 equals, we have here 30. We have 2x equals 24. X is equal to 12. Okay, so this point is 12 and 6. Okay, so we have it there, 12 and 6. So these are our vertices. Okay, so for this one, we substitute these vertices into our objective function, or this equation in the objective function. We have here, okay, z is equal to 180x plus 100y. Okay, so for 15 and 0, we have there 180 times 15, okay, plus 100 times 0, which is equal to what? We have 2,000. We have here 2,700. Okay, what about the next one? We have 0 and 12. Okay, 0 and 12. We have there 180 times 0 plus 100 times 12. We have there 1,200. Okay, what about the third one? 12 and 6. We have here 180 times 12 plus 100 times 6, which is equal to how much? 2,760. Okay, so since 12 and 6 produces the maximum amount of the objective function, therefore the decision must be what? X, our number of tables, is 12, and y, our number of chairs, is 6. Okay, so for a maximum profit of how much? We have 2,760. Okay, so that's it. Another example. This is for minimization. Okay, so here we have a small generator burns two types of fuel. Okay, we have the low sulfur and high sulfur to produce electricity. For 1 hour, each gallon of low sulfur emits 3 units of sulfur dioxide, generates 4 kilowatts, electricity, and costs 160 pesos. You have there. Okay. Each gallon of high sulfur emits 5 units of sulfur dioxide, generates 4 kilowatts, and costs 150. Okay, so the Environmental Protection Agency insists that the maximum amount of sulfur dioxide that can be emitted per hour is 15 units. Suppose that at least 16 kilowatts must be generated per hour. How many gallons of high sulfur and low sulfur must be utilized per hour in order to minimize the cost of fuel? Okay, so again, how are we going to solve for this? Okay, so let us represent the unknown in the problem. We have there, let x, okay, be our number of gallons of low sulfur, and y, our high sulfur. The number of gallons of high sulfur. Okay, so what are the constraints? We have the units of sulfur dioxide. We also have the number of kilowatts, and we are given, of course, the cost. Okay, so for the low sulfur, we have there, low sulfur emits 3 units of sulfur dioxide. Okay, generates 4 kilowatts of electricity and costs 160 pesos. Okay? For the high sulfur, we have there, it emits 5 units of sulfur dioxide. It generates 4 kilowatts also and costs 150. Okay? So, what are the limits or the limits for the sulfur dioxide and of course the electricity? We have the Environmental Protection Agency insists that the maximum amount of sulfur dioxide that can be emitted per hour is only 15 units. So this is less than or equal to 15. But for the electricity, at least 16 kilowatts must be generated. So that's greater than or equal to 16. Okay? So now, our objective function is to minimize the cost that is equal to, we have 160x plus 150y. So subject to, what are the constraints? We have there 3x plus 15 or 5y. We have here 5y is less than or equal to 15. Then 4x plus 4y is greater than or equal to 16. Okay, of course, for our implicit, we have x and y should be greater than or equal to 0. Again, for this one, let's make this an equation. We have 3x plus 5y is equal to 15. So here, if x is 0, what is y? We have 3. If y is 0, what is x? Okay, we have there 5. Okay, for this one, we have 4x plus 4y is equal to 16. If x is 0, y is 4. And if y is 0, x is 4. Okay, so let us draw our graph or graph our constraints. Okay, so for this one, we have, okay, we have 1. Okay. And then 1, 2, 3, 4. Okay, let's make a bigger graph. Okay, so we have there 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5. Okay, so for this one, we have our first line is 0, 3, and 5, 0. So we have it. Okay. There you go. The second one is 4 and 0, 4 and 4, 0. Okay. Okay, you have it there. That's it. Okay, so for the first inequality, we have there 3x plus 5y is less than or equal to 15. So for this one, we shade it like this. Okay. Then for the 4x plus 4y is greater than 16. Okay, so that's greater than or equal to 16. Let's shade it like this. Okay. Okay, so where is our region? It's here. Okay, so you have it there. Okay, so what are the vertices? We have there 4, 0, 5, 0, and what about this point? Okay, again, let's compute for that. We have there, we have 3x plus 5y is equal to 15. We have 4x plus 4y is equal to 16. Okay, so let's eliminate x. We have 4 and 3. Okay, so we have here 12x plus 20y is equal to 60. We have 12x plus 12y is equal to, we have 48. Okay, so we have it here. We have 8y is equal to, we have 12. Y is 1.5. Okay. Then, if y is 1.5, what is x? So, let's say we have it here. 3x plus 5y is equal to 15. So, 3x plus 5 times 1.5 equals 15. Okay? So, we have there 3x plus, wait. We have here, you have 7.5 equals 15. Okay? So, 3x equals 7.5. X is 2.5. This is 7.5. Sorry for this. Okay? So, this point, okay, so if this equation, this inequality is 3x plus 5y is less than or equal to 15. This is 4x plus 4y is greater than or equal to 16. Okay? So, okay? So, this, sorry for that. Okay? So, we have here, okay, this point is 2.5 and 1.5. Okay, so let us substitute it to our objective function. We have here 4, 0, 5, 0, and 2.5 and 1.5. Okay, so we have there 160 x plus 150 y. So we have 160 times 4 plus 150 times 0 is equal to, we have 640. Okay, 640. Am I right? Okay. Then we have 160 times 5 plus 150 times 0. We have there 800. Okay. Then what about the last one? 160 times 2.5 plus 150 times 1.5. We have there 150 times 1.5. Okay, 625. Okay, so that's the minimum cost. Okay, so we have here, since 625 is the smallest value, therefore our decision should be what? We have 2.5 gallons of low sulfur and 1.5 gallons of high sulfur for a minimum cost of 625 pesos. Okay, so for another example, the steel producer makes two types of steel, the regular steel and the special steel. So we have it here, regular steel and special steel. A ton of regular steel requires 2 hours in the open heart furnace and 3 hours in the soaking pit. Then a ton of special steel requires 2 hours in the open heart furnace and 5 hours in the soaking pit. The open heart furnace is available for 8 hours per day, and the soaking pit is available for 15 hours per day. The profit on a ton of regular steel is 4,000 and it is 6,000 on the special steel. So determine how many tons of each type of steel should be made to maximize the profit, considering that demand on regular steel is at least 1 ton. Okay? So this is another constraint. Okay, so let us solve for this problem. Okay, so for this one, of course, we have let X be our regular steel and Y our special steel. We have the open heart furnace, soaking pit, and the profit. Okay, so for this one, for the regular steel, it requires 2 hours in the open heart furnace and 3 hours in the soaking pit. It contributes 4,000 to profit. For the special steel, it requires 2 hours in the open heart furnace and 5 hours in the soaking pit. Okay, so it contributes 6,000 to the profit. Okay, so the open heart furnace is available for 8 hours only. Okay, so that's less than or equal to 8. And for the soaking pit, it's available for 15 hours only. Okay, so our objective is to maximize our profit, that is equal to 4,000 x plus 6,000 y. Okay, subject to, what are our constraints? We have there 2x plus 2y is less than or equal to 8. 3x plus 5y is less than or equal to 15. Don't forget, the demand for regular steel is at least 1 ton. Okay, so that's greater than or equal to 1. And of course, our implicit constraints x and y should be greater than or equal to 0. Okay, so let's make this an equation, or let's make these equations. Okay, so we have here 2x plus 2y is equal to 8. So the coordinates for this is 0 and 4 and 4, 0. For the next equation, we have 3x plus 5y, that's equal to 15. What are our coordinates? We have 0, 3 and we have 5, 0. Okay, so for this one, of course, this is x is equal to 1. So this is 1, 0. Okay, so let us graph our constraints. Okay, so we have, okay, that's 1, 2, 3, 4, and 5. Okay, then we have 1, 2, 3, 4, and 5. Okay, so that's it. Then for the first equation, we have there 0, 4, and 4, 0. So this is our first line. Okay, then for our second line, we have there 3 and 5. Okay, so we have it here. Okay, so this is our second line. Okay, then the third one is 1, 0. It's here. Okay, so we have it there. Okay, so again, these are inequalities. For the first inequality, we have there 2x plus 2y is equal to 8. That's that's less than or equal to 8. We have it here. This is our shade. Okay, the second inequality, that's 3x plus 5y is less than or equal to 15. So we have it here. Okay, then for the last one, x is greater than or equal to 1. We have it here. This is our shade. Okay, so where is our visible region? This one. Okay, so you have it there. This is our visible region. Okay, so what are the vertices? We have 1, 0, 4, 0. Then we have it, this one, what is this point? Okay, so we have, that's 3x plus 5y is equal to 15. X is equal to 1. So if x is 1, we have there 3 plus 5y is equal to 15. We have 5y is equal to 12. Y is equal to, what is 12 divided by 5? We have 2.4. So this point is what? 1 and 2.4. What about this intersection? We have it here. 2x plus 2y is equal to 8. Then we have 3x plus 5y is equal to 15. Okay, so let's eliminate x. We have 3 and 2. We have 6x plus 6y is equal to 24. Then we have 6x plus 10y is equal to 30. Okay, so we have their negative 4y is equal to, we have 6. So y is, we have 6 divided by 4. That's 1.5. So if y is 1.5, okay, let's use it here at this equation. So let's say 2x plus 2y is equal to 8. Okay, so let's say 2x plus 2 times 1.5 is equal to 8. We have there 2x is equal to 5. So x is 2.5. Okay, so we have here 2.5 and 1.5. Okay, so there you go. We have there our vertices. Let us substitute it to our objective function, that is 4,000x plus 6,000y. Okay, so we have here first is, okay, let's say 1 and, we have 1 and 0. So this is 4,000 times 1 plus 6,000 times 0. That's equal to 4,000. The next is 4 and 0. We have 4,000 times 4 plus 6,000 times 0. We have there 16,000. Okay? Then we have 1 and 2.4. So that's 4,000 times 1 plus 6,000 times 2.4. And that's equal to, we have 6,000 times 2.4, 14,000 plus 4,000. It's equal to 18,400. Okay. And the last one, we have 2.5 and 1.5. So we have here 4,000 times 2.5 plus 6,000 times 1.5. And that's equal to, we have 4,000 times 2.5 plus 6,000 times 1.5. We have 19,000. Okay. So, since 2.5 and 1.5 is the highest value, therefore, our decision should be, we have, for the regular steel, we have 2.5. For the special steel, we have 1.5. Okay? For a maximum profit of 19,000. Okay? So that's it. Thank you.